And off we go. So, yeah, we're going to do an entire chapter today in the remaining 40 minutes of class. 37 minutes remaining in class. And this is actually pretty doable because most of Chapter 4 is very mechanical. So there's, here's the process, here's how you do it pretty much. I'm going to spend just a little bit of time talking about sort of the background ideas and why the intuition is really plenty good enough for what you're going to need going forward. So I'm not going to get into, rigorous details and stuff like that. Okay, so a reminder of single variable calculus. You all remember the Taylor polynomial. Let's see here, let me do this better. Taylor polynomial, this thing right here. Good for a lot of things, right? Now, what defines the Taylor polynomial? There's different takes. I think the best way to think about it is that it's the unique polynomial of the appropriate degree that mimics the function you're interested in. It's a copycat. It's a best case copycat function for whatever other function you're trying to approximate. Okay, so in other words, it's got the same value, the same derivative, the same second derivative, third, fourth, etc., all the way up to whatever your degree is. Okay, well, with that in mind, we can do the same thing for multivariable functions. We can ask, okay, what polynomial of degree k mimics f? Again, up to the kth order. In other words, we want it to have the same value, the same partial derivatives, the same second partials, third partials, fourth partials, and all the way up through the kth partials. Now, you got to keep in mind, this is a lot stronger of a requirement because there's not just one first order single derivative of the functions in question. There's a bunch of them, depending on how many variables there are. And second order partials, oh gosh, well there's a lot, there's n squared of those, right? And then all the way up to the kth order, there's endless numbers of those. Okay, but nevertheless, there is a polynomial that will do that. You can always find a kth order polynomial that will meet that requirement. We're not going to talk about the general formula for what does that. I'm just going to show you what we call the second degree Taylor polynomial. This is, in other words, just the first three terms. The first two terms, I hope you won't even be surprised. The first two terms, that's the linear approximation. How about that? Right, very convenient. The only new thing here is what is the third term, the second order term. And this is what it looks like. As it turns out, it's not that hard to check. It's just a matter of kind of writing things down. And what you'll notice, though, is that there is, unfortunately, a dot product in there. And that makes this a little bit harder to kind of deal with. It makes it harder to control. There's more different possibilities. If you come up here to the single variable case and you look at that second order term, right, there's no dot product. This is actually pretty easy to deal with. And this is also kth power. Oh gosh, let's see. Let me replace these with 2's. Real quick. Those having been replaced by 2's, 1/2 is always positive. X minus a quantity squared is always positive. Doesn't do it. And then so whether this term is positive or negative just comes down to looking at the second derivative. And that's why we have a second derivative test, by the way. So this, of course, is a more complicated construction. This is a quadratic form. And I hope that didn't send a chill down the spines of every student in the room from memories of linear algebra studying quadratic forms. The good news is there's very little that we're going to need about quadratic forms from this, and the linear algebra that's not our problem. This isn't a linear algebra class, but linear algebra, as y'all will recall, is how you get your hands on this thing, and we'll talk a little bit more about that in a couple minutes. So the most interesting new part of this is, of course, this matrix. It is called the Hessian matrix, thus the notation. It's defined by that formula right there. It's just a matrix of second partials arranged in the obvious way. By the way, don't forget that when you're talking about an appropriately nice function, which order you do the partials doesn't matter. That means this is a symmetric matrix. And I'll remind y'all know this from linear algebra, symmetric matrices have really nice properties in terms of eigenvectors and eigenvalues and stuff like this. Okay. All right, so which ends up being very helpful. Okay, that's section 4.1. So we're going to make it through this just fine. Let's see, on to 4.2. Again, a quick little reminder of how does this work in single variable calculus. In single variable calculus, if you want to do an optimization problem, you want to find a local maximum, right? I'm going to give you a take on this. I think this is an important point of view, and that is that there is a set of conditions you can write down. Here they are, 3 conditions that allow you to eliminate as being at all possible a point in the domain that might otherwise be viewed as a possible maximum. Because here's the thing: if you have a point in the interior, like let's say like this. Oh, well, let me use this point. You have a point like that in the interior. It's in the interior. If the function's differentiable there, the derivative is non-zero, well, it can't be a maximum. The function is in the process of increasing as you go to the right. It can't be a maximum if it's still getting bigger. Right? Now, you might say, well, what if the derivative's negative? Well, if the derivative's negative, then go to the left, and the function is still getting bigger as you go to the left. And because the point's in the interior, we know that both of these directions are on the table. I mean, you could totally go to the left, you could totally go to the right. So if a point satisfies these 3 conditions, definitely not a maximum. Right, now this is the sort of the deductive element of an optimization process in single variable. And it's extremely powerful. This allows us to eliminate most of the points in the domain. All of those points, all of those points, all of those points, and all of those points. Now, it doesn't allow me to eliminate the boundary points. They're not in the interior. It doesn't allow me to eliminate this point. It's not differentiable. Doesn't allow me to eliminate this point or this point. The derivative there is not non-zero. So there are some points that remain that we can't eliminate by this argument, but it's really helpful. We just eliminated infinitely many points and have a handful of candidates remaining, and then you just deal with it. It's not that big a deal at that point. Okay. All right. So that's this is what we call a critical point. Critical points are simply points where our elimination argument fails. Commonly misunderstood things is that a lot of people think that when you have a critical point, that means you know something about that point. And very importantly, it's quite the opposite. These are the points, the critical points, where we don't know what's going on. All we know is that our elimination argument fails. Those are the throw up your hands, I have no idea what's going on there points. So again, very common misunderstanding. Students think that if you have a critical point, it's got to be a maximum. Okay, maybe a maximum or a minimum. No, it doesn't. Look at this one. That's neither a maximum nor a minimum. Not globally, not locally. That's nothing of particular interest if you're interested in maximizing. If you're interested in optimizing, that is neither, and that's a who cares. Okay. All right. So there is a multivariable version of this elimination argument, and here's the big idea. Again, there are 3 conditions that you can write down, and if those 3 conditions are satisfied, that's definitely not a maximizer. So you look at that point right there. Presuming, as vaguely suggested by the diagram, that function's differentiable. Well, it's definitely in the interior, and the gradient would appear to be kind of that way, which is non-zero, and that can't possibly be a maximum. Look, the function's still increasing as you go in the direction of the gradient. Can't be at a maximum if the function's still getting bigger. right? That's the big idea. So again, that eliminates practically every point in the domain. The only points that we can't eliminate there are the ones where one of these conditions fails. Whoops, I'm trying to get this all on. There we go. So if the point fails to be in the interior, namely the boundary, if the point fails to be differentiable, such as that point right there, if the point fails to have a non-zero gradient, in other words, if it has a gradient of 0, such as there, or there, or there, these are the points where our elimination argument fails. I have no idea what's going on at these green points. So we'll just we'll call them critical points and we'll deal with them separately. And you can see we have a handful of points there in the interior. What we're really going to have to worry about, and this will begin the next section, in other words, in about 5 minutes, how are we going to deal with this infinitely many points on the boundary? That's going to be our real nasty problem. And there's a wonderful method for dealing with it. So when you want to find critical points of a multivariable function, real valued multivariable function, you got to check 3 things. You got to look for points that are on the boundary. You got to look for, again, separate deal, separate method we'll get to later. You got to look at points where the function fails to be differentiable. And you got to look at points where the gradient is 0. The 0 vector, that is. Okay, so. All right, now we'll do an example momentarily. There is the question, though, of, again, what do you conclude when you find a critical point? And as you can see from the picture I've drawn here, again, the fact that it's a critical point doesn't tell you much. It could be a maximum. Or I don't know, maybe it's I can't quite tell as I've drawn it which one of those is the biggest. But anyway, certainly those are both local maxes. It could be a minimum, maybe, I don't know, who knows. It could be what we call a saddle point. That's a weird little phenomenon. There is no single variable version of a saddle point. By the way, I think this should be called a Pringle point. Don't you think they should update the language? I think so. Right? Much more relatable. Who rides horses anymore? Yeah, various different possibilities. And by the way, these are not all the possibilities. It gets weird. When you have a two-dimensional domain, there's a lot of different ways that a function can behave differently in different directions. And my favorite example is what's called the monkey saddle. And this is a pretty good picture of it right here. The idea is it's kind of like a Pringle. This is a deformed Pringle. I feel like I've gotten potato chips of this shape in various situations, but it kind of slopes downward in 3 different directions, kind of upward in 3 different directions, instead of just 2 and 2. And of course, the funnier version of this is this picture right here. You can see why they call it a monkey saddle is because it's got a slope downward for the monkey's 2 legs and for the tail, which is just adorable. So pick your favorite picture, and you could probably speculate there are even weirder versions than this. Why not a spider saddle? Right? The ups and downs could do 8 times as you go around. Right? So lots of weird possibilities. Again, just to emphasize, just because you have a critical point does not mean that it's a maximum. Alrighty, so let's do one. Here we go. Here's a function. I want to find all the critical points. Mercifully, it does not ask us to then classify what kind of critical points are these. We'll get to that later. So, okay, we've got multiple things to check. First, are there any boundary points in our domain? And well, this function is defined on R2. There is no boundary of R2, so there are no boundary critical points. That's nice. Let's see, what about differentiability? Does this function ever fail to be differentiable? Nope. Lastly, where is the gradient equal to 0. And so you get a little system of equations to solve. I need for this to equal to 0. I also need for that to equal to 0. And what you find is there's only 2 possibilities for x, there's only 1 possibility for y, and altogether this gives you 2 critical points. Everybody see how that works? No big deal, right? Here's a common mistake that students make. And again, this is a sort of a special case of one of my broad points that I'm always talking about. Remember, we're not interested in answers, we're interested in reasoning. We need to know all of the critical points, right? And if you skip methods, if you skip conditions, then you are just missing important possibilities, right? You can't draw conclusions about your answers if you haven't checked under every rock, right? You can't know what's under there or what's not under there, right? So a lot of students make the mistake of thinking, you know what? I usually get most critical points by looking at where the gradient is 0, so I'm just going to do that. Right? And that's not okay. You got to check the first 2 conditions as well. Now here's the good news. The good news is these first 2 conditions are usually really easy. Just geometrically, think about the domain and ask yourself if there's a boundary. It's usually pretty self-evident from the nature of the situation. Most of the functions we're going to give you are differentiable everywhere. Just say so. Right? This right here, just having written this down right there, could be worth anywhere from 1 to maybe 3 points. Easy money. Don't leave that on the table, right? Pick up your free points. Go ahead and take them. Right? So don't think of this as something silly you have to do, or else you lose points. Think of this as something easy that you can do to get points. And again, it is part of the process, and you do have to do it. Okay. All right. Now, this algebra was easy. Sometimes the algebra gets a little weirder. Here is a case. Forget about what function this came from, or if this even comes from a function. Let's suppose that when you get down to setting your gradient equal to 0, you've got to do something, I don't know, along these lines. First thing you'll notice is that means x squared is equal to y squared. And big mistake a lot of students make, super common mistake. Lots of students will say, well, that means x equals y. And no, it does not. Straight up not true, right? It's just not true. You've got to consider both possibilities. So it could be that x is y, or it could be that x is negative y. Everybody see the point here? This is one of the areas in which I think a lot of high school math classes do a lot of damage to students by telling them, don't worry about it. That's weirdo, whatever. It's absolutely not. This is just what you have to do. All right, so you got to consider these 2 different cases. First, we'll consider the first possibility, that x is equal to y. If x is equal to y, then that tells us this. And then you can solve for y, and you get y as 0 or 1. And once you know y is 0 or 1, don't forget, we know that x is equal to y, and that gives us then these 2 critical points. Everybody see what happened there? Okay, now again, that was just the first case. You also have to consider the second case. It is perfectly possible that x might be negative y. You got to go down that road. You got to see what's under that rock. Who knows? There might be a critical point down there. This gives you a slightly different equation for y, because you have a different formula for y, for x in terms of y. And so you get different values of y, and in particular, these values of y combined with, keep in mind, x is negative y, gives us these 2 more critical points. Oh, wait a minute, we already had one of them, but still 1 brand new critical point that we would have missed. So our reasoning would have been incomplete and invalid if we hadn't done this second part. How are we doing on that? Is everybody all right? All right, so you got to worry about cases. The second derivative test, in single variable, it boils down to, wrong thing, boils down to looking at the second order term, and as we previously discussed, it's pretty straightforward to figure out at a glance if this term is always positive or always negative. This just boils down to what's the second derivative. So in single variable, the second derivative test is pretty easy. In multivariable, it again boils down to whether this second order term is, always negative, always positive or always negative. But there's a new possibility. It could be that it goes kind of both ways depending on which direction you're moving. And so indefinite is a legitimate possibility. Right? And how do you determine this? Well, we need to decide, we have to figure out how to understand quadratic forms. When are quadratic forms always positive, always negative, or neither? And y'all remember there's a whole thing about that. It turns out that because of some very cool linear algebra, and I encourage y'all to think this through. You don't have to. It's not part of the course. You're not responsible for it. It's very cool how this linear algebra, the mere fact that the Hessian is symmetric, allows for some really neat observations about diagonalizability and eigenvalues and blah, blah, blah. And it turns out that you can streamline the whole process to this little algorithm right here. You have to look at this thing called the Hessian determinant. So the determinant of that Hessian matrix. If the Hessian determinant is positive, then you have a fairly familiar second derivative test. Just look at the XX second partial, see if it's positive or negative. Conclude accordingly. Kind of just like what you would expect. You also have to worry, though, about the possibility that the Hessian might be negative. If the Hessian determinant's negative, you can't use these rules. They don't work. It doesn't make any sense. It just straight up does not work. Right? In this case, you have some sort of a saddle point. Now, I don't know if it's a monkey saddle or a spider saddle or just a regular saddle or maybe some other kind of weird non-extremum type situation. But one way or another, it's a saddle point. And then, of course, it's always possible that determinant might be 0, in which case the test fails, which just means, again, that we don't know what's going on. The failure of the test does not mean that it's not a max. It does not mean that it's not a min. It means we don't know. Is that cool? All right. Okay. In the interests of time and thinking about trade-offs, and again, such a difficult thing given how this course is so packed and we have so much we have to cover, I'm going to let y'all read this example. This is an immediate, direct application of the ideas in this second derivative test we just pointed to. And so give that a read. I don't think you'll find it to be particularly challenging. You just compute according to the little flow chart and get your answer. Yeah?
When the determinant equals 0, what would the graph look like?
Yeah, that's the whole problem, is that it's hard to say. There's just a million possibilities. The mere fact that the determinant 0 doesn't actually help you draw a picture. It just means that there's a lot of possibilities that we can't narrow down. Yeah. Right. Okay. Real quick, with global extrema. Now again, I don't want to spend a lot of time on this one either. But there is a deep question as to whether or not a local max that we may have found might also be a global max. Right? And in the single variable version, there are roughly 3 different ways in which a global max could fail to exist. Right? I don't think these are hard to figure. You look here on this one on the left. The left endpoint is kind of open, and the function just get as big as it wants. Right? There's nothing to stop the function from just getting arbitrarily huge. There is no maximum there. If we have an endpoint that's at infinity, well, again, the function could just keep getting bigger and bigger. If we allow discontinuities, Well, adding discontinuity, the function can just keep getting bigger and bigger. No maximum exists. So it turns out these are representative of really the only ways that a maximum can fail to exist. And so what we have is this theorem that has three conditions. And roughly speaking, these three conditions say if the domain contains its boundary, in other words, if it contains the endpoints, in general, it contains its boundary. If it's a bounded domain, in other words, it's not running off to infinity in any direction. And if there's no discontinuities, if the function's continuous. If these three things don't happen, then as it turns out, yeah, there definitely is somewhere in your domain an absolute maximum value of the function that is achieved somewhere in that domain. It's a very useful fact to know. Notice these conditions are easy to check. And if you know that the absolute maximum exists, just look at your critical points. See where the function's the biggest. That's got to be the absolute maximum. Alrighty. The rest of this section you're not responsible for. Basically, in section 4.3, we're going to find a method that's better than this anyway. Main reason I have all this written out in the notes is so that you can see, a little visual impact of how inconvenient this is. Let's see. Oh, I didn't even. Let's get all of it here. Look how much effort this sort of brute force method is. It's not pleasant. There's a tremendous amount of work to do, and it would be really nice if we had a different way to deal with boundaries. And that's what we're going to see in the next section here on Lagrange multipliers. Okay, so on to 4.3. Let's look at this. Actually, let me zoom in a little bit more. Let's look at this example right here. Find the point closest to the origin. Let's focus on this first part here real quick. Where's the point that's closest to the origin? The origin. That was easy. That's not the question. We're interested in, but just among these points. You're not allowed to pick the origin. The origin doesn't satisfy that constraint, what we call a constraint. Now we have a much harder problem. Looking only at points on this, whatever that is, right? Among just those points, which one is closest to the origin? Hard problem. Okay, so this falls into a category of questions where there are two functions given. There's the function that you want to optimize. This is distance squared to the origin. Real quick observation, if you want to minimize distance, you're also minimizing the square of the distance. A little geometric, right? A little freebie. Easier to work without the square roots. So this is what we want to optimize, right? But there's another function here whose level set, one of whose level sets tells me what my constraint is. And we have a name for this second function. This is called the constraint function. The first function is called the objective function. Second is the constraint function. So what we're going to entertain here now is how do you deal with an optimization problem where you have an objective to be maximized and a constraint function that is not allowed to change. That constraint function, we're constrained to a level set of it. And it is critically important, no pun intended, that this be a level set. Okay, so a couple of quickie examples of what kinds of questions come up like this. Let's look at how to find the box of greatest possible volume that we can make with a given amount of area. Well, volume is my objective, because that's what I'm trying to make as big as possible. and I have a fixed amount of area. So I have an objective function and I have a constraint function. Does everybody see what I mean by these terms and how that applies to this example here? Right? The volume is the function we're trying to make as big as possible. The area is the thing that's not allowed to change. Okay. Similarly, here's a real world problem. Very natural real world problem. I've got a limited budget. Now that's a harsh reality for practically everyone. Okay? Got a limited budget, and look, I'm trying to start a little company here, and I've got to hire some people, and I got to buy some tools, and I got to buy some materials, raw materials, and I'm trying to produce product. How do I make the most possible product, given that I have this, again, very limited budget? I can't go over this is how much money I got, and that's it. Right? So I want to maximize productivity, whatever that is. That's my objective function, and I have a limited, in other words, fixed. In other words, I'm looking at a level set of. I have a limited budget. So my budget, how much money I've got to spend, is my constraint. So this category of questions where you have an objective to maximize with the understanding of a constraint that can't change, pretty broad. I mean, you can see we can answer geometry problems, economics problems. Not hard to see that you can solve engineering problems with this. You have certain constraints in engineering. You want to maximize, efficiency or whatever. Okay. All right. Oh, whoops. So, how do we do this? Super clever idea. Again, I'm mostly going to eliminate points. And the big idea is, if these three conditions are satisfied, that's definitely not a maximizer. It's just a matter of looking at the picture. Differentiability means that the gradients are actually useful and mean what we think they mean. Non-zero gradient of the constraint means that constraint points in the direction perpendicular to the surface. It's got to be non-zero to point in a direction at all. Right? And if the gradient of f is not a multiple of that gradient of g, well, if it's not a multiple, then it has to be pointing what you might call, off the perpendicular. And if it's off the perpendicular, then can't be a maximum, couldn't possibly be a maximum, because look at this vector right here. In other words, if I were to just go kind of along the constraint set, whatever this level set, whatever my constraint set is, if I were to just go kind of in that direction, whatever direction on the surface is suggested by this, off perpendicular objective gradient, well, then the function is increasing. And if it's increasing, you're not at a maximum yet. All right, so again, it's just a matter of looking at points where these three conditions fail. And so just like you would expect, we're going to look for points where one of these functions fails to be differentiable. Our argument crashes and burns. We have no idea what to do there. Points where the gradient does not define a direction at all. My argument crashes and burns. Or points where the objective gradient is a multiple of the constraint gradient. So we are extremely short on time. I have 3 examples I want to show you here. We'll do as much as we can. As usual, I'm going to try to cut to the most useful parts, the stuff that's least obvious. First, I want to point out, you got to identify your functions, right? You want to find the highest point. You're trying to maximize z. We need a level set, right? So our constraint function is whatever we're looking at a level set of. Okay. Next observation I'll make. Don't forget to check the easy ones. Don't forget the easy money. Take the easy money, right? Observe that they're differentiable. It's usually just a matter of saying, yeah, check it out. They're combinations of known differentiable functions, they're differentiable. This is pretty easy. And so just observe it. You don't have to go through, chapter 2 style and, prove continuous differentiability and stuff like that. You can just, if it's in fact pretty obvious, such as in a case like this, just say so. It's all good. Secondly, where is the constraint gradient equal to 0? Well, this is a little bit subtle here. Here's the constraint gradient. It's a matter of taking the gradient. I'm rewriting that as a matrix vector product. It's a little linear algebra. I need to know where is that equal to 0. And again, reminder, linear algebra is awfully handy for how to solve systems of equations like this, or matrix equations, whatever you want to call them. The only solution here is if x is the 0 vector, make sure that you're good with this kind of thing. The fact that the determinant's non-zero, why does that draw this conclusion? Make sure you remember all that stuff about non-singular matrices. So it would be tempting to say, hey, we found a critical point, but in fact we have not found a critical point. Keep in mind, the whole idea of a critical point is that it's a point where we don't know if it may or may not be what we're looking for. Now, our argument has failed, but here's the thing. X equals 0, definitely not what we're looking for. It's not even a candidate because it doesn't satisfy our constraint. I don't need to eliminate it. It was disallowed in the first place. Is that cool? All right, so you got to be careful about this. Don't mislabel x equals the origin as being a critical point. That's definitely a wrong statement, and again, you're going to lose points on that. Okay, the last thing on this example I'll point out, and this might be the last we can do, don't be too fast and loose with your algebra. It's very easy to miss important things. So it's tempting to look at this and conclude this. Cancel the lambdas. Right? No sweat, just scratch it off. Seems like this ought to be true. This is not valid reasoning. It's not. You can't just go around canceling stuff until you know for sure it's not 0, right? I mean, obvious example, if I were to write down 0 equals 0 times 7, can I cancel that 0 and conclude 0 equals 7? Nonsense. This is one of these things that high schools tend to sweep under the rug and not worry about. And again, it's wildly inappropriate, right? I mean, am I wrong? I mean, you can't do that, right? Straight up not allowed. So you have to first, before we claim that we can just go around canceling a lambda, we got to establish that lambda is not 0. And conveniently, that's easy to do in this case, right? Lambda, if it were 0, this third equation would not be satisfied, and that's not possible. So, again, easy money. All you got to do is just make this little observation that lambda is not 0, and having done that, it is perfectly fine to cancel that lambda. Very often, the last step in the process, then, is to just use these relationships to write everything in terms of z, plug that into there, which then gives us this, and then solve for z. And once you know z, that allows you to solve for x and y, and that gives you your critical points. So the algebra is usually pretty quick after you can solve for some of the variables in terms of the others. The algebra on these kinds of examples is a little different with every example. There are 2 more examples that are in the notes here. I hope you'll take a look at them. By the way, you can always go back to my prior semesters. All my old recordings are up there on the YouTube channel. Just go to a different playlist, different semester, and somewhere there will be discussions of these last two examples. I hope you'll take a look, especially this last one. This last one shows that not only will your reasoning be wrong if you're careless with the algebra, you will miss examples. You will miss, in this case, you would miss 6 critical points if you're not careful with your algebra. So please take a look. Okay, enjoyed working with you all this semester. See you on Friday. See you later. And don't forget about attendance if I didn't already get you.